Hello everyone. Today we are diving into the world of stack applications. Stacks aren't just abstract data structures, they are powerful tools for solving real-world problems. Let's explore how stacks can be used effectively in various scenarios. So, what exactly are stack applications? These are real-world problems that can be solved elegantly using the stack data structure. Stacks utilize the LIFO last in first out principle, which allows for very efficient solutions in certain scenarios. Stacks are commonly used in parsing, algorithm design, and even memory management. The diagram shows last in first out principle of stacks with push and pop operations. Let's dive into our first problem, valid parentheses. Given a string containing just the characters like parentheses, curly braces, and square brackets, we need to determine if the input string is valid. A string is considered valid if each open bracket is closed by the same type of bracket, and if the open brackets are closed in the correct order. On the left side, you can see valid examples. For example, parenthesis, parenthesis square bracket curly brace, and curly brace square bracket curly brace are valid. On the right side, you can see invalid examples. For example, parenthesis square bracket parenthesis closing parenthesis, and square bracket are invalid. Let's discuss how a stack can solve the valid parentheses problem. First, initialize an empty stack. Then, scan the string from left to right one character at a time. If the current character is an opening bracket, push it onto the stack. If the current character is a closing bracket, first check if the stack is empty. If it is empty, that means there is no matching open bracket, so return false. If the stack is not empty, pop the top element from the stack and check if it matches the current closing bracket. If it doesn't match, return false. Finally, after scanning the entire string, check if the stack is empty. If the stack is empty, it means all brackets were correctly closed, so return true, otherwise return false. In the diagram, the current scanning position is indicated by green color. We are traversing from left to right. The opening brackets are pushed into the stack. For closing brackets, the top of the stack is popped and compared. Here's the Python code to implement the valid parentheses solution using a stack. First, define a function named as _valid that takes a string s as input. Create a dictionary named brackets to map each closing bracket to its corresponding opening bracket. Initialize an empty list called stack to act as our stack. Then, iterate through each character in the input string s. If the current character is a closing bracket, pop the top element from the stack. If the stack is empty, assign a special character. Then, check if the popped element matches the corresponding opening bracket for the current closing bracket. If it doesn't match, immediately return false. Otherwise, if the current character is an opening bracket, push it onto the stack. After processing the entire string, check if the stack is empty. If the stack is empty, it means all brackets were closed correctly, so return true. Otherwise, return false. Let's walk through an example to see how this works in practice. Consider the input string curly brace square bracket, closing square bracket, closing curly brace. We start with an empty stack. First, we encounter an opening curly brace, so we push it onto the stack. Next, we see an opening square bracket, which we also push onto the stack. Then we find a closing square bracket. We pop the top element from the stack, which is a square bracket, and it matches the closing square bracket. Finally, we encounter a closing curly brace. We pop the top element from the stack, which is a curly brace, and it matches the closing curly brace. After processing the entire string, the stack is empty, so we return true, indicating that the string is valid. Now let's move on to our second problem, next greater element. Given an array, we need to find the next greater element for each element in the array. The next greater element is defined as the first element to the right of the current element that is greater than the current element. If no such element exists, we output -1. For example, given the array 4, 5, 2, 10, 8, the next greater elements are 5, 10, 10, -1, and -1 respectively. Because for 4, the next greater element is 5. For 5, the next greater element is 10. For 2, the next greater element is 10. For 10, there is no greater element, so it is -1. For 8, there is no greater element, so it is -1. Here's how we can solve the next greater element problem using a stack. First, initialize an empty stack and a result array filled with -1s. Then, iterate through the array from right to left. While the stack is not empty and the current element is greater than or equal to the top element of the stack, pop elements from the stack. If the stack is not empty after the while loop, the top element of the stack is the next greater element for the current element. Finally, push the current element onto the stack. By scanning from right to left and maintaining a stack of potential next greater elements, we can solve this problem efficiently. We can solve this in big O of n time complexity. The diagram shows that stack is storing the array elements from right to left. Here's the Python implementation for next greater element problem. First, define a function named next_greater_element that takes an array R as input. Get the length of the array and store it in n. Initialize a result array with -1 values. Initialize an empty list called stack. Iterate through the array from right to left using a for loop. While the stack is not empty and the current element is greater than or equal to the top element of the stack, pop elements from the stack. If the stack is not empty after the while loop, assign the top element of the stack as the next greater element for the current element in the result array. Finally, push the current element onto the stack. After processing all elements, return the result array containing the next greater elements for each element in the input array. In summary, stacks are perfect for problems requiring last in first out processing. They excel at problems involving balanced symbols, expression evaluation, and finding patterns. The time complexity is often big O of n, where n is the input size. Key operations include push, pop, peek, and is empty. Stacks provide elegant solutions to seemingly complex problems. For further practice, consider these problems. Implement a calculator to evaluate expressions, implement a minimum stack with big O of 1 operations, solve the stock span problem, find the largest rectangle in a histogram, implement a queue using stacks, and find the longest valid parentheses. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.